Dan Kleppner's group at MIT began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Dan Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated. We were having a hard time moving forward.
It was time for the next generation to have a go. Two scientists who trained in Kleppner's department moved out west to Boulder, Colorado. They came up with a different approach to the problem. Rather than focusing on the lighter atoms of the periodic table, Eric Cornell and Carl Wyman hit upon the idea of using much heavier metallic atoms like rubidium and cesium. But would using these giants enable them to reach closer to absolute zero?
The idea in the field in those days was that the light things like hydrogen and lithium would be easier. And there were some good reasons for thinking that, but we had other ideas.
Yeah, sort of gut intuition in some sense.
Their plan was to use a laser beam to cool the atoms, a technique that had already been tried at their old lab at MIT. Lasers are usually associated with making things hot, but if they are tuned to the same frequency as atoms traveling at a particular speed, they can make them cold. When the stream of light particles from the laser hits the selected atoms in the gas cloud, the atoms slow down and hence become cold. Laser cooling was a new tool that had the potential to reduce the temperature of a gas to within a few millionths of a degree of absolute zero. But Cornell and Wyman were not the only ones excited by this prospect. A new scientist had arrived at MIT.
It was in late 91 or early 92 that we had an idea how a different arrangement of laser beams would be able to cool atoms to higher density. And it worked. And this was really a trigger point. I will never forget the excitement in those group meetings when we discussed what do we next. Because with higher density, there are many things you can do. Could we now push to Bose-Einstein condensation?
Quetelet used the full might of MIT's funding to build a laser lab to try to make a condensate in sodium atoms.
This is an atomic beam oven. What is wrapped in tinfoil is a little vacuum chamber where we heat up metallic sodium so the metallic sodium melts and evaporates. And it's ultimately the sodium vapor, the sodium atoms, which we tried to Bose-Einstein condense.
MIT, Boulder, and several other labs were chasing the same goal. It had echoes of the race to produce liquid helium almost a century earlier.
As I tell my students today, anything worth doing is worth doing quickly because science moves on and we're all mortal and you want to do things.
While MIT was installing expensive industrial lasers, Carl Wyman had a different approach.
Throughout my experimental physics career, I've always felt that technology played a big part. So if you could figure out a better technology for doing something, it was going to pay off in the long run in physics.
In some cases, he was ripping open old fax machines and taking out the little chip inside that made the laser and showed that you could take these lasers and put them into a home-built piece of apparatus, stabilize the laser, and use them to do spectroscopy and laser cooling.
This is actually our first, what's called the vapor cell optical trap. You can see it's kind of this old cruddy thing, pulled together glass, where we could send laser beams in from all the different directions and have just a little bit of the atoms we wanted to cool.
As well as bombarding the atoms with lasers, they also trap them in a strong magnetic field.
You could have all your magnetic trap coils outside the vacuum system. It's, again, just a lot easier, simpler to do everything.
We would try this sort of magnetic trap, that sort of magnetic trap, this sort of imaging, that sort of imaging, that sort of cooling. All those things we could do without building a whole new chamber each time. We tried literally 4 different magnetic traps in 4 years, instead of having a 3 or 4 year construction project for each one.
By being fast and flexible, the Boulder group hoped to beat their old lab at MIT. But MIT had its own plans. This was a prize they felt should be theirs.
There was a sense of competition, but it was what I would call friendly competition. I mean, can you imagine 2 athletes? They are in the same training camps, they help each other, they even give tips to each other, but then when it comes to the race, everybody wants to be the first.
The rival groups were all using magnetic trapping and laser cooling to cool their atoms. But for the final push towards absolute zero to turn these atoms of gas into the quantum state Einstein had predicted, they needed one more cooling technique: evaporative cooling.
It's just like with this coffee. The steam coming off the coffee is the hottest of the coffee molecules escaping and carrying away more than their fair share of energy. In the case of the atoms, we keep the atoms in a sort of magnetic bowl, and we confine the atoms there. They zoom around inside the bowl, and then the hottest ones have enough energy to roll up the side of the bowl and fall over the edge, slop over the edge, taking away with them much more than their fair share of energy, and the atoms that remain have less and less energy, which means they move slower and slower and start to cluster near the bottom. And as that happens, we gradually lower the edges of the magnetic trap, and always, so there's just a few atoms that can escape, until finally the remaining atoms cluster near the bottom of the bowl, huddled together. They get colder and colder and denser, and eventually in this way evaporation forces the Bose-Einstein condensation to occur. One problem that we kept encountering is that we had to keep the atoms isolated from the walls. We had to have a really good vacuum, and yet if the vacuum is perfect, what is it that you're actually working with? We had to have a little bit of rubidium gas in there, a tiny bit of rubidium gas that we could catch with our lasers and slow down. So we had this wild idea of constantly changing the pressure in the chamber, letting the pressure get higher and lower, and we built a very elaborate chamber with valves that opened and closed and pumps that turned on and off, and it didn't work for beans. I mean, we spent 6 months, wasted, I might say, 6 months on valves opening, closing, pumps turning on and off. The problem is the rubidium gas has a little bit of stickiness to it, and that meant while we were trying to get all the rubidium out of there, that residual gas was heating up the atoms. So eventually, we had to give up on that idea.
By now, the race to produce a Bose-Einstein condensate was intensifying.
At every major meeting, Eric Cornell and I gave talks or talked to each other. We were keenly aware that we were both working towards the same goal.
It's a mixed thing. On the one hand, it's flattering because they're using an approach which we had pioneered and we felt good about that. On the other hand, it made us a little nervous because we want to advance knowledge, but science is a competitive business, and we felt that we wanted to do it first, and maybe that we were entitled to do it first. Although even that's a mixed bag, because after all, we had jumped into the game of the hydrogen people who had shown us so many of the tricks over the years.
At one point during that period, I remember Carl Wyman being quoted in an article saying that He hopes that the MIT group gets there first because they started it all, and so they would get the Nobel Prize, and then the Gilla group could do all the interesting science. Well, that was a very nice thought. It didn't quite work out that way.
In June 1995, the Boulder Group was working round the clock, knowing that several other labs were also poised to produce the first condensate. An official visit from a government funding committee was the last thing they needed.
The standard thing you do when the important people come around is you close down your lab and clean up everything and put posters on the walls so they can see how productive you are. Of course, that's the exact opposite of being productive. We didn't want to close down the lab or clean up our lab or put up posters. We wanted to work very hard. So the senior dignitaries in the three-piece suits and so on came in to the lab, and we left the lights off, and everyone continued to work. And I made them keep their voices down and talked to them rather in a hurried way, and then sort of shuffled them out the door. And they all had a slightly puzzled look on their face, because it probably had never happened to them before in the history of being a visiting committee, that they were treated with as little pomp. And later I actually met one of the guys who said, I suspected something was up that day, because otherwise you never would have dared to do that.
June the 5th, 1995, turned out to be a big day in the history of physics. They had finally made what Einstein had predicted 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here. You know, let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
Condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast, and even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
Wyman and Cornell created the first Bose-Einstein condensate in a cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know. They had reached a temperature of 170 billionth of a degree above absolute zero.
One of the first things you need to understand about Bose-Einstein condensation is how very, very cold it is. Where we live at room temperature is far above absolute zero on this scale. Imagine that room temperature is represented by London, thousands of kilometers from here. Then on that scale, if we imagine right here where I'm standing in Boulder is absolute zero, the coldest possible temperature, then how close are we to absolute zero? If we think of London as being room temperature and right where I am is absolute zero, then Bose-Einstein condensation occurs just the thickness of this pencil lead away from absolute zero.
Within weeks of the Boulder Group's success, Wolfgang Ketterle produced an even larger condensate from 10 million sodium atoms. At last, quantum mechanics was more than just theoretical mumbo-jumbo. It was something that could be seen with the naked eye.